The Minecraft RTX beta has been released and is in your hands. And before I released my video on Thursday this week, covering some of the special things that path tracing can do in Minecraft, I sat down with the developers in the game itself and interviewed them about the development process of Minecraft RTX, how it works, what the challenges were, and what makes Minecraft RTX so special. So without further ado, here is my interview with the developers behind Minecraft RTX. I want to start up with this conversation, and thank you everyone for joining us here today. If you could really quickly just explain who you are and what your position is on this project, Minecraft RTX, I'd be grateful.
I'll go first. My name is Ollie Wright. I'm the lead engineer on the Nvidia side for Minecraft.
So I'm Jakub Bokshansky. I'm a development technology engineer at Nvidia, currently working as an engineer on Minecraft, primarily on ray tracing.
Yeps, and my name is Pauli Ukarainen. I'm yet another dev tech engineer and just working on ray tracing with this project.
My name is Jaakko Haapasalo. I'm producer on the Nvidia side on Minecraft with RTX.
Thank you very much. So before we get into the more technical discussion, I think it's great for our audience to know what exactly path tracing is, because everyone hears about ray tracing all the time. They heard about ray tracing acceleration in RTX GPUs, but what exactly is path tracing? How is it different than ray tracing? And how is it different than the normal Minecraft or normal rendering that we've come to see in games like Minecraft?
I don't think there is a strict distinction between ray tracing and path tracing. Generally, they're very similar terms and sometimes used interchangeably even. But I think that in the past we used to distinguish between ray tracing and path tracing in terms of like you can have one ray traced feature such as ray traced shadows or ray traced reflections, while path tracing is more a global solution to include all aspects like shadows, reflections, GI caustics in one. Using path tracing, it's called path instead of ray tracing because it assumes that you are tracing path, meaning multiple rays between observer and the light to form a path of how light bounces around the scene to create caustics, global illumination, and things like that. And I would say that the biggest change from rasterization-based rendering we were used to before is that things that have to be pre-baked in rasterization, like the probes to calculate global lighting, we can now do them in real time using path tracing. So
what was the genesis of this project? When did it start? And how long has the team been working on it?
Yeah, I'm trying to think of the genesis actually. I think I forget honestly where the original idea or spark came from, whether it was us or Microsoft or somebody else, but we've been working on this since early last year, I would say about March maybe. And then if you recall, we shared some early progress in Gamescom last year, and we've been working ever since to kind of finalize everything and get ready for the beta that's coming up right now. I think one of the things that kind of made this a very interesting project for us, and something that we definitely eagerly jumped on right away, was Minecraft itself, which it's obviously one of the most iconic games ever. That's one thing, and that's very important, but it's also a game that has a very simple premise, which is basically placing blocks and sometimes breaking them, but then you can create practically anything with that very simple premise, and it's user-generated content all the way, if you will, and it has become, as an environment, it's entirely dynamic, and that is actually a very good match for something like path tracing, where you're unable to bake light maps, for example, in a traditional way, where anything can change at any point, and the path tracing will just adapt to that. So we felt that was a very good fit, and I think that was a big part of the motivation.
As you do mention, the game kind of lends itself to being path traced because it is completely dynamic all the time. But another thing that we've noticed, obviously, is coming from Quake 2 being path traced, is that kind of the simplicity of the original graphical presentation is also an aid in enabling path tracing, because you can switch over, from really expensive shading techniques and really expensive character models and things like that in AAA games to have a more simple world and then light it in a very expensive way. So if you could explain a bit or elaborate on it, in what ways does the kind of way Minecraft was rendered previously, before it was under DXR, that aid it being path traced in a way? So like perhaps it's like blocky nature.
I'm not sure there are any aspects of it that make it more easy. You may think so to kind of look at it, because it's very, very simplistic graphics, but it still has everything that you would have in a game with, say, more polygons or more realistic. It's just it's a style that they go for with the 16 by 16 textures and the cubes everywhere. It's a very distinctive style, but that in itself doesn't make anything simpler, if that makes sense. You still got a huge number of polygons going off into the distance. Not everything is cube shaped. You've got the mobs, you've got lots of different shaped objects. So you can't rely on the cube nature of the world for anything. You've got the grass here right in front of you. It kind of sounds simple. Oh, it's Minecraft, it's just cubes, right? But it's not. It's just as complicated to render things in Minecraft as it is for any other game, particularly when we've added PBR materials. So we've got the same kind of glossiness and emissivity and roughness. We've got metallic materials. We've got all the same kind of materials now that you would have in a more realistic game.
Yeah, and we also support higher definition textures if you want to do that. So that's totally possible to mod in.
Yes, and we have also added normal maps and roughness maps.
Basically, taking this from March of last year, let's say, the engine, at that time, I think the Bedrock engine, this Render Dragon version of it, I'm not sure if it supported DirectX 12 at that point in time. Was that something that people in this conversation were involved in, to bring the engine over to DX12 and then DXR on top of that? And if so, could anyone probably explain that process to me and how easy it was? Or
no, fortunately, the Render Dragon engine at that point did support DX12, so we didn't have to worry about that side of it. The only thing we had to worry about was adding the DXR support and the ray tracing.
That's actually pretty great. And so plugging into DXR, like the structures were built out of the geometry without much great work, or was that actually like a large process in itself to making sure that you could actually like see a triangle?
Right. It's I think in the space of 2 or 3 weeks, if I'm remembering correctly. Jaakko might be able to correct me here. I think in the space of about 2 or 3 weeks we had something up and running. We had the acceleration structures being built, and we had, I think, Jakob put together some simple kind of ambient occlusion debug view so we could see the world. So I think that we call it raise on screen, that first kind of milestone when you get to see something. So I think we got to raise on screen in between 2 and 3 weeks. Speaking of DXR, Microsoft just kind of codified and announced DirectX 12 Ultimate. Part of that is DirectX Ray Tracing 1.1. This beta version of the game, does it use any features like inline ray tracing from DirectX Ray Tracing 1.1? And if not, does it plan to in the future? And if it does, or if it will in the future, what areas of the current path tracing do you imagine that DirectX Ray Tracing 1.1 features could be of great benefit or of some benefit? If I understand correctly, I don't think DXL 1.1 is available in a full release of Windows yet. I think it's available in one of the kind of early access builds. So we've written this all around 1.0. Everything works really well in 1.0, and we're quite happy with it. We're using dispatch rates for everything. Could we refactor to use 1.1? Possibly. I don't know what benefits we would get from that.
I think Jakob had some ideas about light sampling that might have used some of that stuff, so I think we're looking into it.
Indeed, we are looking into it, but we don't have any specific results yet.
Yeah, and it wouldn't be playing a major role, at least what we think now.
What are some advancements, very specific advancements in terms of like graphical effects that you can see in Minecraft RTX that were not available in Quake 2 RTX, and what are the reasons for that in the engine? Like, what are you doing differently in the path tracing now?
That's a good question. So I think the multi-bounce GI, we have diffuse global illumination that has multiple bounces.
There's a form of it, I believe, but I think we have a different way of sort of caching and propagating that might be more advanced.
The irradiance caching is, I don't think that is actually in Quake 2 RTX at all. Like, what does the irradiance caching essentially do, and why is it such a benefit?
The irradiance cache effectively stores ray tracing data with the geometry in the world. So normally with your ray tracing, you would be tracing for each pixel. You would like trace a primary ray into the screen, and then you would trace secondary rays from where you hit. This kind of does the ray tracing in the world from the geometry, and it stores data with the geometry in Minecraft. One of the things that allows us to do is accelerate our secondary rays a lot in cases when we don't need a lot of detail. So there's a performance aspect to it, and it also gives us this feedback mechanism. We shoot rays from the geometry in the world and they hit other parts of the world, and you get this feedback going on, and that's what gives it the multiple bounces. Now there is a lag in there, so if you place a block down, there'll be a little bit of a delay as you see it filling in, as you see the light bouncing around. Most of the time that isn't an issue in Minecraft, so it's tailored to work with the kind of geometry that we have here, and the scale, the resolution of it fits very well with the kind of scale of geometry that we have in Minecraft as well. It's a kind of a pragmatic solution to a problem of how to get that multiple bounces and how to get a bit more performance at the same time.
So the irradiance cache looks to, I'm pretty sure, bounce around diffuse lighting primarily. And if I recall from like the Metro's global illumination, that's Metro Exodus's global illumination in implementation, that they kind of stored the global illumination in a spherical harmonic, and they could reconstruct specularity from that for the global illumination. How many real specular bounces of global illumination are there in Minecraft RTX?
Okay, well this kind of depends on how smooth the surface is. So if you've got something like a mirror here that Jako's standing in front of, then we will do, I think, up to 8 bounces. If it's not perfectly smooth, then it's the primary hit and then the secondary hit, and then we will stop at the irradiance cache. So it's just kind of 2 rays.
For like a mirror surface like this, are these rays all being cast in the span of one frame, or are they accumulated over 8 frames?
In the mirror case, that's all in one frame. But it's kind of there's a change in behavior as soon as you get to this kind of mirror case.
Yeah, if you stand between these two kind of polished mirror blocks, you can see multiple bounces going off, 7 or 8. And
then like if you get to the 8th one, you can see like a dark black box. It looks like almost.
Yeah, the mirror. Yeah, it eventually tends to the dark. Yeah.
Another feature that you added in too, I think, was basically how the volumetric fog was lit, which I think is actually very unique. I hadn't seen that before, and it surprised me that it was there when I saw the game at Gamescom.
The technique that's in there now is using a voxel-based approach. It's a common technique in rasterized games at the moment, where you have a 3D grid of voxels, but it's aligned with the frustum. So they're called fruxels or froxels, right? And then in each of those froxels, you figure out the light that's coming into there and how much of that light is being inscattered towards the viewer. And then you have another pass where you ray march, where you kind of walk through the froxels and accumulate all the inscatter. The difference with what we're doing here is that the bit where you figure out what light's coming in to the froxel, that's ray traced. Normally you would go for a shadow map. Problem with shadow maps is they are typically on or off. You either hit the light or you don't hit the light. So you can't do coloured shadows. With the ray tracing, it's quite easy to change your shadow lookups to do coloured shadows and have semi-transparent shadows. So rays can go through semi-transparent materials and change the transmission of the light that's going through. It's quite easy to extend this technique to be full colour and have full coloured shadows.
That is particularly interesting, and I'm looking at this kind of setup rainbow that you have right here. Another kind of part of that is that something that was only added in Quake 2 RTX's like 1.3 patch, I'm pretty sure, was the ability for glass to transmit color through as light goes through it. Could you explain just really quickly how it is done in Minecraft RTX, both for water and also how it is done for something like these glass blocks right here, because that's a very stark feature that is pretty rare to see in real-time rendering at all.
There's a feature called an AnyHit shader, where you can trace a ray, and the AnyHit shader will get called for potentially every intersection of a surface with that ray. So that will get called for all of your, say, semi-transparent surfaces. So we have a transmission, it's called, transmission color for each surface. It's basically what color the surface is. It's like a light filter. So a red filter would have a transmission of 100, so it lets 100% of the red light through and 0% of the green and the blue light through. And you just accumulate that transmission. You actually multiply them together. So each surface that the ray goes through, you multiply the transmission values together. If you've got light coming from a glowstone or a torch and it hits a surface, then we shoot a transmission ray, like a probe, to figure out what's the total amount of transmission loss between that surface and the light source.
And does it work differently for the water surfaces in Minecraft, or is that like the exact same AnyHit shader style technique?
The water is slightly different because you want to have transmission loss through the media. So the glass blocks are handled slightly different. Glass blocks are handled like a clear glass block with coloured filters on the surface, on the faces. But the water, you want to see that kind of ray getting attenuated as the light goes through the water. So water is handled slightly differently for that reason, but it can get a little bit complicated figuring out the order that you're hitting things, because the AnyHit shaders can come in any order. They're not guaranteed to come in the order that you're going through the ray. So there's a little bit of trickery, and there are things where the game will know when the camera is underwater, for example. So when the camera is underwater, all of the primary rays are going through water. So they will all experience the transmission loss and the extinction, it's called, for water. So water is handled slightly differently.
So bringing over Minecraft to, this DX12 version of it, and at all getting it to work, I imagine required you setting up like the game to have motion vectors, because either it would need TAA or it would need the motion vectors for denoising, or specifically for DLSS. Was anyone on the team responsible for that, and was that actually a hard thing to do to make Minecraft suitable with like having temporal information over time, or was that relatively easy?
So I guess many of us were involved with that process, because basically the game doesn't know about previous frame, and obviously for motion you need to know where you were in the previous frame and where you are now in the current frame. We definitely needed to do something special just for the ray tracing implementation to know like which object was present in the previous frame and where is it now. To not to go into too much detail, let's just say now it kind of works. But so it works well enough. We have a way, but it's probably something that we need to look into for the full release still.
Okay, yeah, because playing it now, I actually don't see that much like ghosting on a lot of objects, and the fact that DLSS even works at all and with any level of competency says that it's working well, whatever you're doing exactly.
We can say that we basically need to track like each object that is on the screen and if it has been there on the previous frame and so forth. So
I was like each object like given an ID or something like that?
Yeah, basically like that.
Part of that, obviously, getting DLSS to working and the obviously getting the path tracing to working and have it be functional. A big portion of path tracing is not just the shooting out and tracing of rays themselves, but also the denoising, which in this game specifically costs more than the actual like the ray tracing loop. Could you explain exactly what is actually a large portion of that cost exactly? Why is denoising so specifically expensive in a game like this? And what are some of the the optimization strategies that you took towards making the denoising as have the cost that it actually has?
Why do we spend so much on denoising, and why is it so hard? We have in Minecraft quite a noisy signal. GI is shooting rays in all directions. It's effectively randomly sampled, and that accounts for skylights and for emissive surfaces and for any kind of lighting from bounced light. That means it's possible to get very kind of noisy signal. If you have one bit of glowstone that's quite a long way away from your surface, then the chances of the rays hitting that get quite low. And that means you have what we call a very noisy signal, which means you need a good denoiser. So we do spend a lot on denoising. The denoising, the process it goes through it's an iterative solution. You spend many iterations with a filter kernel that gets bigger and bigger and bigger each iteration, and the job of that kernel is to look at samples nearby, say, is this sample on the same surface? Is it part of the same object, the same polygon even? And is it a good candidate for sharing information with this pixel? It's a very bandwidth heavy operation. I think we do 6 iterations for the diffuse denoiser.
Yes, we do 6 for both specular and diffuse.
So that's 6 iterations with the kernel getting wider and wider each time. The filter kernel ends up covering quite a large area to be able to take that noisy signal. So if you just get one bright spot, we need to be able to potentially share that signal with lots and lots of pixels. It's an expensive thing to do. I'm sure there is still scope for optimizing it further, but that's where we are now.
Speaking of the denoiser, really quickly, it is done in 3 separate denoisers, as far as I understand, for like the shadows, the specular, and the diffuse lighting. Can you explain, basically for the viewers, why it is a good idea to separate like the denoising for each of these elements?
I let Paola talk about the sun shadows. But for the diffuse and specular, probably the biggest reason is the way that they move differently. So if you move your viewpoint, the diffuse stays with the surface. Think of the light has kind of been stuck to the surface, but the specular is a reflection, and that kind of moves with the reflection point. So that's the main reason why you want to treat them separately. And also we're denoising the light signal, not the final image. So in the data that we're denoising, we don't have, say, the surface color, the diffuse albedo, the green pixels. So it's a much smoother signal that we finally end up that's denoised, and then we have this final combined step that puts everything back together and brings in the diffuse albedo, the metalness, and it puts it all together to kind of help the denoiser in the things that we're denoising. Even the normal maps, we're denoising spherical harmonics for the diffuse. So we've got spherical harmonics in screen space, which makes the job of the denoiser easier because it doesn't have to stop with normal maps. Different normal directions in a normal map, the diffuse denoiser doesn't need to worry about. It's only interested in the geometry normal. That can make its job easier as well. Paola, do you want to talk about the sun?
Basically for the visibility, which is shadows, we use a different denoiser, and that's just simply because we can use a different denoiser which can be more specialized for shadows and also faster. At first, we had the visibility signal in the, what would you call it, global illumination buffer, and we just denoised everything all together. By doing that, we lost some shadow detail and that very, those hard shadows. Because obviously, what we see now on the screen, when you are very near some edge, you can have very hard shadows, but when you go further, you can have very soft. And by separating the shadow from the global illumination data, we could obviously denoise them separately, and then we could use things like the sun size projected onto the surface, and we could figure out there where the shadow should be very precise and hard and where it should be soft. By doing this separately, we get a faster solution, which is also better quality because it's basically specialized for this particular task.
Part of that global illumination pass and denoiser after the primary visibility with the sun, the normal, emissive surfaces are also added into that. So do they get technically, if you add a whole bunch of emissive surfaces in an area, would the quality break down for the lighting there, or does it scale up really well to thousands of lights, let's say, for example?
We have a distinction between emissive surfaces and what we call explicit lights, and I'll let Jakob talk about the explicit lights in a second. So the emissive surfaces, it actually works opposite to what you just said. The more emissive surfaces you have there, the easier it gets for the denoising, because the signal is cleaner. There is more chance of hitting an emissive surface because it's bigger, there's more of it. The explicit lights work the other way around, so they're torches and end rods and lanterns, things like that, which are small lights instead of the big size of blocks. Jakob, do you want to talk a little bit about how that works?
Yeah, sure. So, as Oli mentioned, we handle the emissive triangles and lights just by standard specular and diffuse passes. But explicit lights, such as torches and lanterns, let's say, we have a special pass for them, where for each pixel we randomly select one torch or one lantern, and we shoot the ray towards it. If you think about it, in each pixel we sample a different light, and then we feed it to Denoiser for denoising. So even if we have thousands and thousands of torches, we still randomly sample each one of them at least sometimes. And the final image is quite noiseless because of Denoiser does a very good job on this. And maybe I would add about denoising. You have been asking before of why is denoising so expensive and why it's necessary. So maybe one technical observation is that, like Oli mentioned, we have quite a noisy signal. But if we wanted to have less noisy signal in the beginning, we could shoot more rays. But pretty fast we will hit a law of diminishing returns. So if you double the ray count, let's say you shoot 2 rays instead of 1, the noise goes to half. But if you want to halve it again, you have to shoot 4 rays, and then halve it again 8 rays. So pretty soon you end up in a situation that is just not feasible to shoot thousands of rays per pixel, and your noise is not getting much lower anymore. So that's why denoisers will be probably for foreseeable future a big part of these games.
Talking about the denoising, one thing that was floated right when the Turing cards were announced, or RTX cards were announced, was the possibility to use machine learning for denoising. As I understand, in this game, it's like spatially and temporally done.
I know there's a whole bunch of research going on. I'm not sure specifically for Minecraft when that would become relevant. We're definitely looking into that. They're kind of artificial intelligence denoisers, as far as I know, and I'm not an expert in this particular field. They're being used a lot already in kind of offline rendering, and I think there's a lot of research going on relating to that and bringing them into real time. But
I would say one thing that I notice right now in the game, obviously talking about performance, is that it does run actually pretty well for being a full-on path tracing experience. But one thing I experienced at Gamescom when playing that build back then was the fact that increasing the size of the world chunks, as in Minecraft, so those areas that are kind of rendered out from the player's center point, would dramatically affect performance. But I was just playing around with the game earlier and noticed that changing that rendering chunk distance to make it be further away from the player origin didn't actually affect performance that much as I experienced back then. So what is the reason why it now runs decidedly better, essentially, than what I experienced back at Gamescom?
Well, this turned out to be a memory issue. So the performance drop that you were seeing on the Gamescom build was when there were some aspects of the system that were very, very inefficient. And as we were creating more and more chunks, the amount of memory just ballooned, and it oversubscribed the VRAM. So as soon as you get a situation where you've got things that are going out to system memory, then performance can take a big hit. So it falls off a cliff. So a lot of those issues have actually been addressed. It still uses more memory than vanilla Minecraft, obviously, but it's not as bad as it was. So we can go to higher chunk distances now than we could previously. So it's actually more of it was falling off a cliff for the memory rather than it being a ray tracing restriction, as it were.
Do the rays shot out into the distance shade at the same level of detail as the ones that hit things closer to the camera, or do things shaded at a distance are they shaded more primitively?
It's all to do with the distance between where the ray is launched from and the thing it hits. So the rays that are in the distance have exactly the same shading as the ones that are close by.
One thing that's particular to this, and I noticed in the presentation as well, was the reference to the fact that the primary visibility could have been done through rasterization, but here it is done through ray tracing. For what reason did you choose to do that initial step through ray tracing, and what advantages does it bring actually, since you did do that?
We did it through ray tracing, probably initially through laziness. That was just we were just getting our arrays on screen, and that was the thing to do. And it would have actually been a little bit more work to use. We would need to modify the Minecraft rasterizer to output a G buffer, so that it's not free. There would be some work to do there. And then later on, we discovered things like the lenses and things like that we can do in our raygen by shooting primary rays that actually would be trickier to do. Maybe it was the right decision. We could always do the very first hit with rasterization, and maybe we will look to do that in the future as an optimization. To be honest, it's not going to make a huge amount of difference.
Yeah, that was kind of the surprising finding we had.
The primary raygen is pretty fast because the rays are coherent. Everything's going in the same direction. Neighboring rays hit the same kind of thing, so you don't hit some of the bottlenecks that you do in other passes.
So right now the game ships in this beta form with a lot of these really interesting path tracing systemic things being visible, like the transmission, the volumetrics, like the shadows attenuating into the penumbra in the distance and things like that. But what other kind of more experimental or interesting features do you think that this path tracer is capable of doing in the future that are currently not in the game? Are there other ways you've looked into extending the path tracing?
One of the things we have that's actually working, that's not shipping in the beta, is we can, as well as having the sunlight going into the volumetric fog, we can put global illumination data in there as well. So anything that's kind of glowing will also light up the fog. You'll often see this in games now with like point light sources that are able to illuminate fog, but we can have this from anything that's bright, whether it's emissive or whether it just happens to be bright from it being lit by the sun. So this is something we're very hopeful that we're going to get into the game before the full release.
Are there any other like specific features like the caustics themselves from the water or something like that? I know they're currently in right now, but like multiple bounce caustics or something crazy like that.
Yeah, the caustics we have right now are pretty simple. We've toyed around, I guess. That was a point of discussion at some point where we could do something like mesh-based caustics or so. I think that's more on a level of a crazy idea at this point, but you never know. There's multiple things.
Things like that might come down to how much performance we can get back by release. There'll be a big push, I think, to try and do more optimizing and get more performance back. And anything we can do there can be plowed back into more features.
So speaking of things that, obviously this is a beta product right now, what are some things at the moment that you think are like behind or you would like to see improved, like specific things in terms of the path tracing?
You want me to call out the bugs?
Yeah, I mean, you could call it, just say the things that you would like to see improved, I guess I would say.
Or what would you keep improving, I guess, is a more positive way of putting
it.
Right?
Yeah, what kind of things would you keep improving on from this beta form?
There are things that happen that everybody is going to see that are plain ugly that we don't like. For example, if you place a torch or you remove a torch at night, then there's some quite nasty ghosting that goes on in the because there's that temporal lag. There you go. That's not pretty. We know that's not pretty. So we've certainly got there are techniques that we can use to mitigate this a lot. So things like that.
Would that be a change to the denoising then, or like being more aggressive with the irradiance cache, or what exactly would that mean?
This one is a denoising issue, specifically that issue. This would involve making the denoiser adaptive, so have the denoiser be aware that the lighting has changed and become more responsive during that time. There's a similar issue in the irradiance cache that we see with the it's what we call a chunk culling issue. The Minecraft is built for rasterization, and rasterization only cares about what you can see on the screen. The world is built out of chunks, these kind of 16 by 16 by 16 block units of the world. So they've got this clever system for culling chunks and only having chunks in the scene that are visible. That's obviously no good for ray tracing because we have other things that impact what you see on the screen. You could have a chunk that's casting a shadow from the sun that you would want to consider. So we've had to do a bit of work in that area to make the chunk culling more suitable for ray tracing. Instead of just considering what's on screen, it also considers what's behind you, for example, in case it's in a reflection, or what's nearby, and things which are kind of going out towards the sun that might be casting a shadow onto the scene. But it's not perfect, and there are issues with it. If you go down into any cave, you get this issue sometimes where you'll see a bit in the distance where it looks like the cave is glowing. It looks like there's some skylight in there, and that's exactly what it is, because a neighbouring chunk has been culled. So while it's down there, it's kind of flooded with skylights, and then when you walk up to it, that hole gets plugged, as it were. Skylight can no longer get into it, so it then goes down to its proper dark solution. So that's a particular issue that I really would like to be fixed before release. But it's not easy. It's not easy to know which chunks are going to have an effect like a visible effect on the final image, because you could say that every chunk will have some impact on the final image, but some of them are just going to be so tiny that it's not worth having. And you don't want to have all the chunks which are kind of in the some visible range in the acceleration structure, because that's impractical. So you need to find some middle ground. That's the kind of hard problem that is not so obvious, I think, when you just look at the results.
It's a circular dependency, because you have to shoot the rays to know what will be visible, but after that it's pointless to cull because it's already too late. You already shot your rays. So it's this kind of problem.
Switching to more positive things, other than just like speaking of negative things, because this already looks obviously really amazing. One thing that I found really interesting was reading through the presentation. I'm pretty sure the only rasterized bits are maybe like the initial sun surface and the particles in the game. Can you explain how like something like the particles are blended in with the scene at all?
Yeah, there's nothing fancy there actually, so we just simply blend them. Some of the particles will check if they are like when you just normally rasterize them in Minecraft. They will know if they are behind something or something is blocking them from some parts or they are in front of something. So we kind of get a buffer that has like correctly rendered, or in this case rasterized particles, and we just simply blend that with our ray tracing final result. Nothing fancy there. I guess I would really like to say that this is maybe something that we would like to improve, because sometimes you might see weird things happening with it, but mostly it's working pretty well.
Do they get any lighting contribution from the environment?
I don't think we try to match the lighting. Minecraft itself does the rasterization coloring a little bit differently based on the time of the day, I think, so that's where some matching comes from.
The sun and the moon actually currently, I think they are ray traced.
Yep, it's a mesh, just a billboard, a quad, and it's ray traced as if it was an object in the scene.
Do you see the techniques used in this version of the game to be able to be used in other projects in the future? Because it seems like this built obviously off of previous work on denoising and the path tracing system as well. Do you see this also, these denoising techniques, for example, working in a game that has like more fine detail as well, like with higher geometry counts, or like, you know, like things that are like more sparsely rendered, like hair or something like that? Do these techniques also apply very well to games with more complex graphics, I would say, in terms of visual noise?
I think the techniques that we use are not that specialized for Minecraft, so they are working in other, let's say, research projects or other games as well. So I think that's pretty cool that they are not that specialized for this content.
Yeah, that is one very nice thing about path tracing, that it's much more general, I think, than rasterization, which you have to fine-tune. Let's say for a first-person shooter, you have to fine-tune it differently for real-time strategy. And the nice thing about path tracing is that it is very general, and the same algorithm can be adapted to many different scenes and many different kinds of games easily, I would say.
From everyone here worked on different portions of this, obviously. I would love to hear from each one of you what specific thing you worked on and what part of this project you were specifically proud of while working on it.
Ollie, you want to go first, or Jakub, or who?
Yeah. So I worked on the initial ray tracing implementation of diffuse and specular passes, including the material, and I'm very happy how that worked out in terms of visual quality of the material. The physically based material, I mean.
So basically I joined way later than Jakub and Ollie, and one thing that I did first was shadow denoising, and I think that I like the most, because it kind of turns out as I wanted it to be. So finally something looks as it's supposed to. And then I did just a bunch of stuff like making sure that everything just works. Ray tracing works with the bits and pieces that we rasterize, etc., and some other experiments with denoising.
Yeah, I forgot to mention I worked on implementation of torches, so that is also a very cool thing.
I think one of the big things that I worked on early was the irradiance cache, getting that implemented, and really quite pleased with how that's turned out. in particularly the multiple bounds nature of it. I think that really helps in this game. When you see pools of lava in the cave, you can just see a kind of a faint glow from some caves, and you walk up to that glow and then you realize that the lava flow is kind of round a corner a couple of 100 feet below you. I think that's really cool. I think one of the things I discovered was that I lose a lot of time to just messing about in Minecraft. I'll be implementing a feature and then I'll go and test it, and I'll discover that I've maybe just spent an hour just building something because it looks cool. So I've been having too much fun on this project. It's been good.
Yeah, I guess like it's a challenge, but it's also a good thing that we were finally working with a project where we can actually modify the test scenes. Like usually when you're working on a game, you might have a team of artists doing the scene or doing the final scene or the textures, but now we can do it all. But then again, like it's a challenge because we need to prepare for it. There might be somebody who might put millions of lights and like thousands of layers of transparent blocks or whatnot, which is not normally seen in especially like AAA games. So yeah, I guess it's fun.
One of the things blew me away was I think you saw some of those curved mirrors and lenses. I think that came about pretty late in the game. I think Ollie just fooled around with it one day and showed it to us, and nobody had really planned for that or really designed for it or tested it, and it kind of flat out just worked. And that was a kind of a aha moment for me on path tracing, I guess, that, you know, there is a system of rules behind it and it is consistent and it can lead to interesting discoveries. So that kind of blew me away at the time.
Jaakko, Olli and Paula mentioned all my feelings about this. It's just amazing to play it and play around with it, just to build stuff and immediately see what ray tracing does with it. We actually can modify shaders in runtime, so you can build something and then fine-tune it by editing the shaders. So it's very rewarding for a developer to just be able to build anything as a test world immediately and see the results.
One last question. This probably won't be in the video at all. I'm just curious, why can't you actually in perfect mirror reflections or in any reflections see the Steve character, your first person character model? Is it just because it's not rendered at all when you go into first person?
Yeah, basically just because we just didn't get to it yet.
Oh.
Yes.
Okay.
So yeah, you would have to do some special things to render that, because that is not actually properly rendered in the scene since you're in first person, right? So we'd have to kind of just create an exception for that. We just didn't get to that yet, so that's definitely something for the full release. You can see, if you go into third person mode, you can see your character model just fine, but not in. You can see your hand in the first person mode, which is kind of weird, but
which is very funny looking.
Better than nothing, maybe, or maybe not.
There are a few little things like that, I think, aren't there? I think the third-person characters get culled early. I don't think we've gotten around to that code either.
Yeah, it's
so if you're in a
culling, yeah.
game and you've got mirrors, then if another player goes off your screen, they'll vanish from the mirror as well. So there'll be little things like that will get fixed for the full release.
Very, very cool. I guess I would say thank you to everyone in the call right now for coming in and taking the time this evening to talk to me about this. And that's it. And hopefully you enjoyed this interview with the developers, on the Nvidia side at least, for Minecraft RTX. And if you did enjoy this video, hit that like button and subscribe to the channel. If you're already a subscriber, then please consider hitting that little bell in the corner to be informed as soon as Digital Foundry posts a video. If you want to see more content like this in the future, interviews with developers, please consider supporting us on Patreon to get our videos at the highest quality available for download. If you want to talk to me about Minecraft RTX or this interview, write a comment below or follow me and Digital Foundry on Twitter. And as always, this is Alex, bidding you farewell und auf Wiedersehen.